Let's go ahead now and move into our math review. Now, what I'm about to discuss should be familiar to you. Maybe a bit rusty, but we're going to discuss things like significant figures, dimensional analysis, unit conversion, and we'll go on to a final discussion of standard deviation, which may be new, but that should be the only thing that's new here. So whenever we're doing measurements, we're really describing the physical properties of matter. So things like mass and volume, if we were to measure those are what we call extensive properties. Those depend on how much material there is. Obviously, more stuff means more mass. Same with volume. More stuff means more volume. Intensive properties would not be dependent on the amount of material, but would be intrinsic to that particular substance. And one of those is density, which will be the subject of your lab next week. Density is simply mass divided by volume. And as mass goes up, volume goes up. So the density of any material is going to remain constant, irrespective of how much you have. Now, what we're going to talk about are mathematical calculations that you perform using measurements. And density is a very simple example of that. You'll measure mass, you measure volume, you take the ratio of those two, and density then is the result of a mathematical calculation based on your measurements. The precision of the calculated result is going to depend on the precision of your data. So it will be necessary, since your calculator doesn't know the difference between a calculation that is just simply mathematical and a calculation involving data, doesn't understand things like precision, you're going to have to round your answer that's given to you by the calculator, because your calculator will just spit out as many digits as it has places to spit. So for example, if I'm performing this calculation on my calculator, I ended up with 1, 2, 3, 4, 5, 6, 7 decimal places, and that's obviously way more precise than either one of my measurements. So it's going to be important for you to understand that the calculator is not going to give you your final result in chemistry. You're going to have to do some work after that. So what we're going to talk about from here, based on this particular example of density, is precision and accuracy, as well as how to get the significant figures of any sort of calculation that you do using data. Now let's quickly discuss the difference between precision and accuracy. Precision simply refers to repeatability. So it has nothing to do with how close your answers or your data would be to any sort of true or known value. It's simply how repeatable your measurements are. So if you were to use a balance that gives you weights out to 0.001 grams, you might expect, as you perform several measurements of mass of the same object, that you might see a little bit of variation in that last decimal place, the fourth decimal place, but you really shouldn't see any more than that. So that would mean you're repeatable very closely around that fourth decimal place of grams. Now, accuracy is different. Accuracy does mean the deviation of your data from the true value. Now, sometimes you'll know a true value, and sometimes if you're doing original research, of course, there would be no true value that would be known. So really all you have to fall on with your measurements is precision. And the presumption will be that if your instruments are well calibrated and your measurements are precise and very repeatable, that if you average those measurements together, you should get an accurate data set. And that's really the best we can do in science. Now let's talk about significant figures. I think that kind of puts a little terror into most students' hearts, and really not with good reason. But what it all means is, how precise is your information? So a significant figure means a figure that would be included in the precision of that measurement. So significant figures are going to be important because they'll come up in any calculation that you do with data. So in a scientific calculation, for example, the one we just talked about with density, the density can't be any more precise than your least precise input. So let's repeat the measurements that I showed on the previous slide. Mass of an object, 52.0298 grams. The volume of that object was 49.6 milliliters. Now in this example, the mass has 6 significant figures. All of those digits are significant, and it's precise to 0.001 grams, or 1/10,000th of a gram. The volume, 49.6 milliliters, has 3 significant figures. Now what that means is that I have 3 digits of precision in my volume, 6 digits of precision in my mass. So when I take the ratio of those two, the density can't be any more precise than the least precise measurement, which was volume. Now, the calculator is going to spit me out a number like 1.04898879. I'll know that my units are grams over milliliters because I'm keeping track of units. Your calculator won't do that for you. It will be necessary for me to round the information given to me by my calculator to reflect the true precision of the density based on my data. Now, my calculation of density is going to be limited by my least precise input, which is volume. It will be limited to 3 significant figures, so it will be necessary to round my density answer to 3 significant figures. So I'll round that 1.04898879 grams per milliliter to 1.05. So this is going to be my final answer, 1.05 grams per milliliter. There's my units, and that will be 3 significant figures. Now we talk about rounding. Again, this should be a review, but the way you do rounding is to go out to the last decimal place that you'd like to keep and go to the next one over. So for example, when I'm rounding this number, 1.04898879, I know that this digit, the hundredths place, is the last one I intend to keep. So in rounding, I'm going to look at the next one. The next one over, if that next digit over is 5 or greater, I'm going to round this digit up. If this digit is less than 5, I'm going to round this digit down. So in this example, 1.04 and then an 8, I would need to round the 4 up to 5, which is why my final answer is 1.05 grams per milliliter. In these examples, if I want to round 3.6595 to 3 significant figures, the last one I keep is the 5, the next one over is a 9. I'm sorry, if I'm going to round this to tenths place, the last one I'm going to keep is this one right here. I look at the one over, it's 5 or greater, so that means I'm going to round up, and my final answer will be 3.7. If I'm going to round this one, and again, let's say the last digit I want to keep is tenths place, I look at the next digit over, that's a 3, that's less than 5, so I'm going to round down, which means my final result is 3.8. Now, one very important thing, there's a reason why this is in red, and why never is in caps. You never round your data. Your data is whatever precision that you were able to obtain when you conducted the data. I'm not going to round 52.0298. I'm not going to round it to 52. I'm not going to round it to 50. I'm not going to say, yeah, to hell with it. It's close enough to 100. That's crazy. I'm given 52.0298 as my precision. I want to keep all of that information. So in my data, I'm never rounding. The only thing I'm ever going to round are calculations that result from a mathematical equation involving data. So for example, with the density is a calculated number. It's the ratio of mass divided by volume. That's an example where you would need to round. So never round your data, only round the results of data calculations. Let's talk about how you determine the number of significant figures. Now, if all of your digits are not zeros, or a 0 is in the middle of a number sandwiched between 2 non-zero digits like a 2 and a 9, then all of those digits are going to be significant, and you simply count how many digits are there, and that's your number of significant figures. Where the number of significant figures needs to be looked at more carefully are where your numbers either begin with zeros or they end with zeros. So we're going to call the numbers that begin with zeros numbers that have leading zeros. We'll talk about numbers that end with 0 as having trailing zeros. So let's first talk about what happens when you have leading zeros in front of the first non-zero digit. So in this example, I have 0.008135 grams. So a very precisely measured mass, but it's also a very small mass. So I have 3 leading zeros here. And it's not really necessary to put this first one in. I usually do put in the 0 in front of the decimal place just because sometimes it's hard to tell the difference, particularly in your notebook, whether a dot is a stray dot or a true decimal place. So I have always gotten in the habit of putting that 0 in front of the decimal place, although it's really not necessary. And notice when I change this to scientific notation, that becomes 8.315 times 10 to the minus 3 grams, and all of those leading zeros have disappeared. So in this number, it's very obvious to see I have 4 significant digits, and it's helpful to express that in scientific notation because now I can see that this one also should have 4 significant figures or significant digits. The thing about the leading zeros is they're placeholders. They have to be there. I can't take them out. I can't simply express this number as 0.8135. That's not the same thing. So they're placeholders. They must be there. You can't remove them, but they don't add any precision to your information. This is 4 significant figures. My leading zeros will never be significant. Let's talk about the case of trailing zeros. Now here there's 2 cases. The trailing zeros may be left of the decimal. An example would be something like 63,500 pounds. And trailing zeros left of the decimal, again, are never going to be significant. Now, if I look at this example, 63,500, I can't leave the zeros out. I can't make it 635 pounds. That's something completely different. So while the zeros must be there, they're important placeholders, they don't contribute any precision to the information. My last most precise digit is in hundreds place, so I would say that this is precise to approximately 100 pounds, which means that this 63,500 pounds has 3 significant figures. Now there will be some cases where your zeros that are left of the decimal will be significant, and in those cases you'll have to tell the reader that. There's a couple of ways to do that. So let's say, for example, that I have information that's accurate to tens of pounds, and I want to tell the reader that this particular digit is significant. The way I can do that is to put a bar above that 0, and now this would be 4 significant figures, the 6, 3, the 5, and this 0, which is marked as significant. The other thing I can do if all of the trailing zeros are significant is I can just simply put a decimal point at the end. So this one, 63,500 with a decimal place, that would tell me that both this 0 and this 0 in the tens place and the ones place are both significant figures. So this particular number, 63,500 followed by a decimal point, would have 5 significant figures. Let's talk about the last case of trailing zeros, and that's where the zeros are right of the decimal place. Now here we're going to have to go by convention. Let's look at this example. This one has both a leading 0, which is not going to be significant, but it has 2 trailing zeros. Notice that these 2 zeros right of the decimal place don't really need to be there. There's not going to be any difference if I write 0.536 or 0.53600. The result would be the same. So the presumption, since these particular zeros do not need to be there, but I did put them in, that must mean that they're significant. I wanted to tell my reader that this trailing 0 right of the decimal place was an important part of my precision. So because both of these zeros are right of the decimal place, this particular number, 0.53600, has 5 significant figures. So make sure you understand the difference between the significance of trailing zeros left of the decimal versus trailing zeros right of the decimal. Now let's talk about how you would determine the number of significant figures to keep in a calculation that you perform using either multiplication or division. Now remember, this only applies to data calculations. An example would be our density calculation that we did a little bit earlier, mass over volume. That's a division problem. The precision in multiplication and division is going to be determined by the number of significant figures in my least precise input. So let's take an example. Let's take this one, 123.5 seconds. So here we go, 123.5, that's 4 significant figures, times 2.58 centimeters per second. This number would have 3 significant figures. When I multiply them together on my calculator is going to give me 318.63. I can see that my seconds in the bottom here will be canceled by the seconds here. So my units, my calculator will not keep track of those. I'll have to do it myself. The units will be centimeters. But this information, this calculated result has 5 significant figures. That's way more precision than the actual outcome can have. Now notice that my two numbers together, the first one is 4 sig figs, the second one is 3 sig figs. That means the result of that calculation can be no more precise than the least precise input, which is 3 significant figures. So I need to round this final result from my calculator to 3 significant figures. The last digit I'm going to keep is this one. I look at the one to the right, which is greater than 5, so I'll round that up to 319 centimeters, and that's going to be my final answer. This comes from my calculator. Units I have to keep track of, rounding and significant figures to get the proper precision in my calculated information I have to keep track of as well. So a couple of things your calculator are not going to help you with: units and significant figures. Let's take another example. Here I have 64,000 inches, and because each of these trailing zeros is left of the decimal, they're not considered part of the precision. This is precise only to the thousands place. So my 64,000 inches has 2 significant figures. This conversion factor, 2.54 centimeters per inch, has 3 significant figures. When I multiply those two together on my calculator, I get 162,560. I know that the units are centimeters because the inches in the bottom here cancel the inches here. But this calculated result can't be right. I have to round it. Now, I have my least precise input at 2 significant figures, meaning I need to round this one to 2 significant figures as well. The last digit I can keep is this one. I look to the right of that. It's smaller than 5, so I'm going to round that to 160,000. So anything after the 6 disappears, and I'm now rounded to 2 significant figures. So it's fairly easy, as long as you're keeping track of the number of significant figures in your input, in a multiplication and division problem, to determine how many significant figures to keep in your final answer. Let's look at what happens with data precision when I do addition and subtraction. The outcome and the method is very different than we just talked about with multiplication and division, where the precision of the output is the same as the precision as the least precise input. In other words, they will have the same number of significant figures. Here, rather than tracking the number of significant figures in my input, what I'm looking at is the number place. So let's take an example. Let's suppose I have a truck that when it's empty weighs 63,547 pounds. Now that piece of data is precise to 1 pound. There's 5 significant figures in that input. Now once I load the truck with cargo, the cargo weighs 58,312 pounds. That too is precise to 1 pound in 5 significant figures. When I add those together, the result, 121,859 pounds, is also precise to 1 pound, but now you'll notice there's six significant figures. And this can happen fairly often when you're adding two numbers that are fairly close together. It will often happen that you'll end up with more significant figures in the answer than you had in any of your inputs. And that's simply because you've added a number place to the left and you've still maintained the same precision, in this case, to ones place or 1 pound. Now, exactly the opposite can happen with subtraction. Let's take this case. I have a small weighing pan, which I pre-weighed 1.258 grams, and then I put a small bit of compound in the weighing pan, and the new weight is 1.271 grams. To find out how much compound I put in, I want to take the difference between those. And when I do that, I end up with 0.013 grams. Now, each of my inputs is precise to thousandths place, or 0.001 grams. Each of my inputs has 4 significant figures. Once I take the difference between those, that number 2, 0.013 grams, is precise to 0.001 grams, or thousandths place. But notice that now I only have 2 significant figures. So I've dropped from 4 sig figs to 2 sig figs. And the reason for that is I'm subtracting two numbers that are fairly close together. But once again, this is a common result that will happen with subtraction. You'll almost always end up with fewer significant figures in your answer than you had in either of your inputs. Let's look at a more complex calculation than the ones we've done thus far. In this example, I have multiplication, division, addition, and subtraction all present. Now, it's fairly common that you'll see calculations like this as you do your exams, your labs, and your practice problems. It's rare that a calculation will involve just a single operation like addition, subtraction, or multiplication, division. The way you approach a problem like this is to not worry about rounding any of the intermediate steps along the way. Wait till you get to the very end to get what your calculator gives you, and then round only one time. So in this case, I'll take 34.72, I'll multiply by, in parens, 1.853 grams plus 284.3 grams. Then I'll divide by, in parens, 91.08 milliliters minus 6.7 milliliters. When I do that without any rounding on the way, my calculator gives me 117.7439222. The units are grams over milliliters. Now, clearly that answer has way more digits of precision than are represented in my data. So I need to go back and figure out how to round it to the appropriate number of digits of precision. The way I'm going to do that is to clear my problem of the additions and subtractions by looking at them individually, determine how many significant figures they represent, even though I'm not actually going to round them. So for example, let's take a look at the numerator. I have 1.853 grams, which is precise to thousandths place, 284.3 grams, which is precise to tenths place. My least precise input is the 284.3 grams, with precision to only tenths place. So were I to stop my calculation there, I would actually have to cut off at tenths place and end up with only 4 significant figures. Now, I'm not going to actually do the rounding. I only want to do that once at the end, but I have to represent that 286.153 as being only 4 sig figs in my ultimate answer. Let's do the same thing with the subtraction in the denominator. 91.08 milliliters is precise to hundredths place. Subtract 6.7 milliliters, which is precise to only tenths place. My least precise input is that 6.7 milliliters, meaning that I would have to cut off my answer to get this as a final answer at tenths place. So even though I'm going to keep 84.38 in the denominator for now, I have to realize that that represents only 3 sig figs in my ultimate answer. At this point, because I've evaluated the additions and subtractions, all I have left is multiplication and division. So I need to just look at my least precise input and round my final answer to that number of sig figs.
The number out front, of course, represents 4 sig figs, so my least precise input is that denominator with only 3 significant figures. What that means is I need to round my answer to 3 sig figs. So 117.7, my 4 sig figs is 7, which is greater than 5, so I'll round up, and I get 118 grams per milliliter, which is my final answer rounded to 3 sig figs. Again, I didn't round along the way, I rounded only once at the end.
Now let's move on to a topic of units and doing math with units, which is something we're going to call dimensional analysis. Now, it doesn't need to be said, but I'm going to say it anyway. And again, red type, all caps, underline means something. All measurements must have units. It's going to be meaningless without them. What does that mean? If you turn in an exam and you've left the units out, I'm going to ding you for it, right? So if you wrote down 137 instead of 137 grams, minus a point. If you wrote down 21.8 and left out the milliliters, minus a point. 137 by itself is meaningless, as is 21.8. You have to put in the units. Very important. Now, dimensional analysis means that we're simply going to do math and keep track of the units. Remember, your calculator doesn't do that. You're going to have to do that yourself. The calculator knows numbers. It doesn't know precision, and it doesn't know units. So let's take a simple conversion factor problem. Let's suppose I want to convert 38.7 centimeters to inches. The conversion equation, the relationship between inches and centimeters, is here. So 1 inch equals 2.54 centimeters. Now, in terms of significant figures, 1 is considered to be exact. It's not going to contribute any significant figures. We can consider that even to have an infinite number of significant figures. 1 is 1. This one, however, is based on a measurement. So 2.54 centimeters contributes 3 significant figures. Now, here is my relationship between inches and centimeters that I need for my conversion. When I create conversion factors, there's 2 possible ones that I can create. I can put 2.54 centimeters over 1 inch, or I can put 1 inch over 2.54 centimeters. Let's go back up here. Remember the relationship. These two equal each other. So that means that these ratios, whichever way I write them, will both equal 1, right? This over this equals 1. This over this equals 1 because they're the same thing. The only difference is the units are different. So now what I want to do is to start with 38.7, multiply by the appropriate conversion factor, and the way I'll choose which conversion factor to use is by canceling the units I want to go away. I want centimeters to disappear, and I want inches to result. So I'm always going to start a problem like this with my starting information, and then I'm going to multiply by a conversion factor, and my result will be some number of inches. I need to now select which of these conversion factors to use, this one or this one. I want to cancel centimeters and keep inches, so I'm going to select the one on the right. I plug that in. The centimeters cancel. I'm left with units of inches. I do the math, multiply those two together. This is what my calculator gives me. So the calculator contributed 15.2362205. I contributed the inches, right? I had to determine what the units were. And now I have to round the result of that calculation to reflect that my input information is 3 significant figures, and my conversion factor is also 3 significant figures. The last digit I can keep is right here, 3 significant figures. The next one over is smaller than 5, so I'm going to round this to 15.2 inches. The final result, 3 significant figures. Now, this sort of conversion factor problem, as I mentioned in my Chem 42 class, comes up over and over and over again in chemistry. So one of the very most important problems you're going to run into. So you'll need to know how to do these problems very well. We're going to give you a little bit of practice and hopefully dust off the cobwebs and shake out the memories that you have from your introductory chemistry class that you took before. Let's talk about another case, unit conversions when the units have an exponent. Let's take this for example. Here I have 148.6 square centimeters, which I write as centimeters to the second power. And I want to convert that to square inches, which I'll write as inches to the second power. Now my relationship I had, which is the one I had on the previous slide, 1 inch equals 2.454 centimeters. Neither one of these is squared. It's simply inches to the first power, centimeters to the first power. This is the only equivalence that I have. So the two possible conversion factors will be this one or this one. Now, as always, with any problem, I'm going to start with my information that I was given, 148.6 square centimeters. I multiply by a conversion factor, but now, since I want inches squared and centimeters squared, I have to square the entire thing. I can't just square the units without squaring the numbers. I have to square all of this. So my conversion factor, because my units are squared here, my entire conversion factor will be squared as well. And when I distribute that, the square distributes to everything. It distributes to the inches, it distributes to the 1, it distributes to the centimeters, and it distributes to the 2.54. So all of that has to be squared separately. Now I can see that by doing that, I have square centimeters here, which will cancel square centimeters there. My final result then is to take 148.6, multiply by 1 squared, divide by 2.54 squared, and the result that my calculator gives me is 23.0330461. That's what my calculator contributes. This I contributed because my only units left are square inches, so that goes here. And then I have to round. I have 4 significant figures here, 3 significant figures here. Remember, this is exact. So my limitation is 3 significant figures. My last digit I can keep is this one. The next one over is less than 5, so I round down. My final answer is 23.0 inches squared, 3 significant figures total. Let's talk about another problem that comes up a number of times in chemistry. That's where you need to string together a number of conversion factors, not just one. An example would be converting 88.4 meters per second of velocity to miles per hour. Now there are several conversions that need to be done. I need to convert meters to miles, and I need to convert seconds to hours. All right, meters to miles, seconds to hours. Now here's my set of conversion equations. 0.62137 miles equals 1 kilometer. The 1 would be exact. This would contribute 5 significant figures. 1 kilometer equals exactly 1,000 meters. And again, I would consider both of these to be infinite. This is not a measurement. It simply is kilo modifying the meters, meaning 10 to the third meters, 1,000. My other relationships are also exact. 60 seconds equals 1 minute. Each of these an infinite number of significant figures. 60 minutes in 1 hour. Each of those are also an infinite number of significant figures. So the only contribution I have to significant figures in all of this is 5 sig figs here, 3 sig figs in my input. So let's see how I'm going to do that problem. Now, one way to do a stacked unit like this, 88.4 meters per second, is to recognize that that's the same as 88.4 meters over 1 second. This is my starting information. I'm going to write it this way and then do my conversion problem. So we'll start here, 88.4 meters per second. Now I can choose to either start with the meters or charge with the seconds. I'm going to start with the meters. So my first contribution comes from this conversion. I take the ratio of those two. I want to cancel meters. So I'm going to write kilometers on top, meters on the bottom. And now I'm ready for my next conversion. I want to convert from the kilometers that remain into miles. So I'm going to go back up here to this relationship. There's the equivalence. I want kilometers to go away. So this goes here, and the miles will be on the top. Now, miles is part of what I want to keep in my final answer. Remember, we're trying to convert to miles per hour. So that part of the units are done. Now I'm going to convert my time units. I have the 1 second over here that I need to go away, and I need to replace it by an hour. So we'll take the first step, my 60 seconds over 1 minute, based on this equivalency. The seconds will cancel. Now I need to convert minutes to hours. So I want to cancel the minutes and leave the hours. So here is my final result for this particular portion of my calculation. So when I go through and cancel all the units, you can see all I'm left with is miles and hours. I do all the math, 88.4 times 1 over 1,000 times 0.62137 over 1 times 60 over 1 times 60 over 1. The result of that comes out of my calculator, here's what my calculator contributes. 197.744789. I have to contribute the units, miles, hours. There's my final units. I have only 3 significant figures in my input. That's going to limit my result to 3 significant figures. The last digit I keep is this one. The next one to the right is greater than 5. I'm going to round up, and my final answer is 198 miles per hour. Let's finish up the discussion of unit with a discussion of prefixes. Now, I took this table from your book, but there's a number of prefixes which are multipliers of units that I want you to remember. Now, these are going to be important, so I'm going to ask you to memorize these. The first is giga or giga, which means 10 to the 9th times whatever follows. So, for example, gigahertz or gigahertz, or gigabytes per second, would mean 10 to the 9th times whatever follows. Mega, abbreviated capital M, is 10 to the 6th times whatever follows. Kilo, as in kilometer, would be 10 to the 3rd times whatever follows. So kilogram, kilometer. Deci means 10 to the minus 1 times whatever follows. Centi, 10 to the minus 2. Milli, 10 to the minus 3. And the last 3 are micro, nano, and pico. So there's 9 of them that I'd like you to remember, and I'd like you to be able to work with their abbreviations. So there will be some memorization required, but this is going to come up over and over again in your career, which hopefully is going to involve science from here. So you might as well get used to using them. So make sure that you understand those 9 prefixes and how to use them.
Let's talk about errors in data and our data calculations. Error is a fact of life in scientific measurements. You want to, of course, try to minimize it, and there are ways to do that, but we have to acknowledge that error will be present and find a way to quantify it. There are a couple of different types of errors that we're going to deal with. One is systematic error, which is the more insidious kind. Usually happens when one of your instruments is out of calibration. What it causes to happen is even if you take several measurements, that you're going to end up on one side or the other of the true value. So anything that's a systematic error is going to affect accuracy of your final answer. Then there's random error, which is always going to be present. It's unpredictable in the sense that it could be perhaps a little bit larger than the true answer or a little bit smaller. But the nice thing about it is because it will be clustered around the true value, if you average enough data points, you should be able to eliminate most of your random error. So random error really only affects precision or repeatability and really shouldn't affect the accuracy of your data. Now we're going to measure each of these in a different way. Let's look at systematic error first, which we'll measure by a quantity called percent error. The percent error formula is to take the average value from your data minus the actual value. Take the absolute value of that. So your numerator is always going to be a positive number because of these absolute value signs. You'll divide that difference then by the actual value. So the only way to find the percent error is if the actual value is known. You'll multiply that ratio then by 100%. Let's take an example. Suppose my data average is 7.18 grams per milliliter. The actual is 7.454 grams per milliliter. plugging that into my systematic error formula, I have my average value minus the actual, absolute value of that divided by the actual times 100%. When I do that, my calculator gives me 4.7745%. There were a few extra digits there which I cut off, but already 4.7745 has more digits of precision than any of my inputs. So I know I need to round that answer. The way we'll do that is to look at the subtraction in this numerator first, figure out how many sig figs it represents, and then I can figure out my overall precision from there. Looking at the numerator only, I see 7.18 minus 7.54. Each of those is precise to hundredths place, meaning my answer will also be precise to hundredths place. But notice that my answer is only going to have two significant figures. I'll of course eliminate this minus sign because of the absolute value. So the numerator in my percent error calculation represents 2 sig figs, 3 sig figs down here, meaning my final answer has to be rounded to 2 significant figures. When I do that, I get 4.8%. So that's our calculation of systematic error using the measure of percent error. For random errors, we're going to use a different measure called the standard deviation.
The formula for standard deviation looks like this. Now, we're going to do this in terms of mathematical symbols, and then we're going to give a real life example to make this make a little bit more sense. So let's take a series of points. We're going to represent them by y, and we're going to give them an index. So this y sub I means the ith point in my set of y values. So I is going to be a simple whole number index, 1, 2, 3, 4, 5, however many values I have. So if I have 5 values, I would have 5 values of y sub 5. So if n equals 5, that's my total number of values in my data samples, I would have 5 values of y sub I. The notation we're going to use for an average will be y with a bar over the top. We'll call that y bar. That'll represent the average of my 5 values, and you know how to calculate an average. You simply add all the values together and divide by how many total values there are. So getting y average is something very easy. The standard deviation is a little bit more of a calculation. Now, standard deviation of a sample is given the symbol of a lowercase s, and that's going to equal the square root of this sum. Remember, the summation means sum, and I go from I, my first value, up to n. So if I had 4 values, that means I would have 4 values of this particular thing. Now notice what this is. This represents each of my sample values, and this represents the average. So this is never going to change for any of the calculations I'm about to do. Well, this would depend on which particular data point I'm looking at. Then I'm going to take this difference and I want to square it. Now, why do I do that? I want to square it because I want that number to always be positive. I don't want my negative answers to cancel out my positive errors. That doesn't tell me anything. And I'm not going to divide as I would with an average by the total number of points, but I'm actually going to divide by n minus 1. And then I'm going to take the square root of that whole thing. So let's see how this kind of complicated equation would work with a... All right, so let's look at a real live example. This is 4 length measurements that I've measured. So these length values represent my y values. I have 4 of them, 5.8 millimeters, 6.1 millimeters, 5.9 millimeters, and 6.2 millimeters. This would represent y1, y2, y3, and y4. If I take the average of those, I would add these 4 together and divide by 4. So my y bar would be 6.0. So now if I come down here to my standard deviation calculation, underneath the square root symbol, I have 4 values of this particular calculation to do that I would need to add together and divide by n minus 1. So let's see how that would work. I have 4 values of y. I have my y bar equals 6.0. My total number of values, n, equals 4. So let's see what that looks like mathematically. And we'll step through this. My first y value, y1, is 5.8. So my first number that I sum is 5.8 minus the 6.0, my y bar. I square all of that. My second value is 6.1. So my next sum would be 6.1 minus 6.0, all of that squared. My third value, 5.9. 5.9 minus 6.0, square that again. My fourth value, 6.2. 6.2 minus 6.0 squared. So I have four things that contribute to the sum up here, determined by my four values of y. This is n equals 4. I subtract 1. So now I have this complicated ratio that I have to take the entire square root of. So let's see how we would do that. Let's first evaluate what's inside the parentheses for all four of these calculations. So 5.8 minus 6.0 is minus 0.2. 6.1 minus 6 is plus 0.1. 5.9 minus 6 minus 0.1. 6.2 minus 6 plus 0.2. Now let's square each of these values. Minus 0.2 squared is 0.04. 0.1 squared is 0.01. Minus 0.1 squared is also plus 0.1. 0.2 squared is 0.04. When I add these together, I get 0.10 and divided by 3. 4 minus 1 is 3. I take the square root of all of that, and I have the square root of 0.033333. Do that on my calculator, and what I find is my S value is 0.1826 millimeters. Now, where did the millimeters come from? My standard deviation is going to have the same units as my inputs, right? My inputs are millimeters up here. I have no data down here. So my final answer will also be in millimeters. And notice that the precision of my inputs only go to tenths place. So each of these measurements, or these subtractions, will only contribute 1 sig fig, right? 5.8 minus 6 minus 0.2. That contributes 1 sig fig. So each of these will only contribute 1 sig fig. This is infinite. It's a count. That's not going to contribute. But my overall significant figures will be just 0.1, or at to 0.1. So that means the last decimal place I can keep is here. The next one over is larger. So when I round my final answer, I have my standard deviation is 0.2 millimeters, rounded. My y bar is 6. So the way I would express my average is 6.0 plus or minus my standard deviation of 0.2 millimeters. All right, so at this point, I think you have everything you need to know to do your math worksheet. So we'll go ahead and complete that and send you on your way.